All right, welcome back, guys. So where we last left off is on the ISIS PDU types. So we'll go ahead and go into that. So the ISIS PDUs are similar to the OSPF message types. Um, so the first one we'll talk about is the intermediate system to intermediate system hello PDUs, or the IIHSs. Those are pretty much your hello messages. Your link state PDUs, which is similar to your link state advertisements between OSPF neighbors. That's used to exchange information and put entries into the link state database. And then your sequence number PDUs, which we'll go into more details on what that does, but it ties into the link state database. But essentially, your hello messages, they are exchanged between systems with ISIS enabled. The messages contain the system ID of the sender, the area assigned addresses, and then the identifier and the identity of neighbors on that circuit that are known to the sending IS. There's some additional information that actually is in the hello messages, as well as the uh, the networks as or the connected interface that the hello messages are actually sourcing from. There's some additional, but those are the main pieces of the PDU that you should know from the IIHS packets. The link state PDU advertises its neighbors and destinations that are directly connected to the IS. It's uniquely identified by the following: the system ID of the intermediate system that generated the LSPDU. I meant to put that, but I put IS. The pseudo node ID. The value is usually 0, except when you're dealing with pseudo node LSPs, and we'll talk about that when we get into the circuit types. It's primarily talking about multi-access circuits. The LSP number, and then the 32-bit sequence number. Um, and then the sequence number, it contains a summary description of one or more LSPs. So the routers that are participating in that area, it'll actually have a description of the circuit IDs in the information per LSP for the LSPDUs. Um, the two type of SNMP, there are two types of sequence number PDUs for both level 1 and level 2 routing. You have your completed sequence number PDUs, which are your description of all your routes and networks. And it used to send a summary of the LSD PDs that an IS has for a given level. So it gives you the full database topology of that given level for level 1 and 2. And if you have multiple adjacencies, you'll have two different set of CSMP, CNSPs, and then you have your partial sequence numbers, which is used to send a summary of a subset of LSPs for a given level that an intermediate system has either has in its database or needs to obtain. And it's also used for acknowledgments in multi-access segments. Your circuit types, similar to the you can correlate this to the OSPF interface network types. So it supports two different circuit types. You have point-to-point and you have multi-access. So point-to-point are pretty much self-explanatory. It's used for directly connected ISIS adjacencies. It utilizes point-to-point IIHS PDUs with the system ID value of 0. And in a later video, we'll actually show you guys some packet captures, because if you do a capture for ISIS packets, you'll notice that some headers will not be there that you'll normally used to be seeing for like BGP, EIGRP, or OSPF, because it uses the CLMP protocol for transport. So I want to give you guys a brief description of what that looks like and what those messages are actually built as. And it's the Cisco default for serial interfaces. Multi-access, it's the default for Ethernet interfaces, and that's kind of similar to your broadcast network type for OSPF. It's used for multi-access segments forming ISIS adjacencies. It utilizes LAN IIHS PDUs with the system ID value of the pseudo node for the system ID value. So what that means is kind of similar to the with OSPF, you have your designated router. Um, ISIS has that same concept with the pseudonode, and the pseudonode is actually called the designated intermediate system, which means that if you have four routers sitting on the same Ethernet segment, and if technically all four routers should not be distributing LSPDUs between each other, the pseudonode designated the DIS will actually be distributing those PDUs amongst the systems. Um, it's better for traffic management and also for bandwidth management. So one of the things is that there is no such thing like with OSPF, how you have the BDR. There is no concept of a backup designated intermediate system. But there's features that are built into ISIS that if you do lose the designated system for that segment, they have things like nonstop forwarding that can actually still allow packets to traverse the network without having to, while the control plane reconverges and the data plane not be affected. So in that case, there are certain things, criteria that are built into ISIS that can prevent that from happening. Like I said, the DIS is similar to the DR and OSPF broadcast types. Multi-access segments, this is negotiated for each level between neighbors and becomes the distribution point for LSPDs. Already went over that. Let's see. Oh, and one of the things to keep in mind is that if you have a level 1-2 adjacency going between your routers, essentially you're going to have a DIS for each level. So level 1 will have its own, and level 2 will have its own. It'll have its own SPF topology associated with it. The DIS is also responsible for sending periodic CSMPs, which means that it's pretty much using it's the synchronization, but it keeps the synchronization happening between all the routers participating on that Ethernet segment. So one of the things I wanted to talk about is the multi-area examples. How I said that you can actually configure a intermediate system with multiple areas and still allow communication to happen. So this is a topology that I actually have configured now. And in testing this, one of the things that I thought would have occurred, which would definitely occur in something like an OSPF or anything like that, if you have multiple areas, say this is, we notice here, let me get my pen out. So we notice here, this is area 49.000.000.002, and then we have 49.000.000.000. So we'll just call this area 0, area 2, and area 1. Because this is area 0, please keep in mind that this has nothing to do with LSA propagation because it does not have the same concept of backbone area. Like OSPF, it's just an identifier. So because this is area 0 and it's bordering between 1 and 2, that's not what is allowing the actual communication to happen between the routers. But in this case, and this is kind of what I explained in the example, I'm an ISP. I bought out another ISP. We're both running ISIS in our core, and I need to start merging our networks together and make it into one ISIS topology. So router 6 is actually going to be used as the border between both areas. And within the configuration, what I'll do is I'll configure two nets, which I did do actually. I configured two network entity titles, one being in area 0 and the other being in area 2. And what's going to happen is I have two level 1 adjacencies happening between router 7 and router 5. Now, he will exchange and process all level 1 LSPDs known with known area 49.0.0.0.2, and he'll actually process the same thing with all 0.0.0.0. But because the actual link state database is built based off the level, not the area, what's going to happen is that you're going to have full synchronization between router 5, 6, and 7. So router 7 actually sees the same topology table as router 6 and 5, even though it's in different areas. It's kind of a hard concept to grasp around, get your head around if you're so used to OSPF, because as we know, each area contains its own link state database. With ISIS, it's done by level, so you can have multiple area identifiers configured and still have synchronization. Now, this isn't something that you would do as a design principle to go out and do this with a full blown design. This is only really supposed to be happening in a case of, like I said, an ISP merger or a company merger, or if you want to change the nets and start consolidating into a single area. So essentially, once all router 7 gets configured with the new area 0, I can eventually delete this area identifier and everybody is on the same area. Um, and another thing that's pretty cool is because it shares the same link state database. Router 7 actually will, so with router 5's level 2 adjacency between XR1, what's going to happen is what's going to happen is router 5 is actually going to generate a default route that's going to get propagated through the level 1 database. So router 7 is actually able to get over to router 2 using the default route that router 5 supplies, and vice versa. Router 2 would actually be able to communicate with router 7 due to the fact that router 1 is going to create that default route that router 2 is going to use to actually traverse it. There are things that you can do as far as route leaking is concerned if you want to see specific prefixes in the level 1 database, but that's outside of the scope of this presentation, but that is a possibility. So like I said, if you want to do the default route but then also have specific prefixes for things like maybe MPLS for label forwarding, you'll have that ability so that R7 and R2 can technically build LSPs and actually have labels or links, label switching paths between each other via each other's loopback addresses, and have the loopback address within the routing table so that LDP can actually generate that label. So that's something that is a possibility. We'll go ahead and stop here and we'll move to the next slide in another video. Let's see. Let's stop.